Okay, this week we're going to talk about air pressure. So, we got to understand what air pressure is. The significant question this week is really the difference between horizontal and vertical variations in air pressure and just the influence they have on the weather. So, let's go down here a little bit to where we can talk about what is air pressure. Air pressure is a force, and a force is just a mass times an acceleration. The mass is the air molecules. They weigh something. May not be a lot, but they weigh something. And the acceleration is when they're moving in the direction or whatever against something. Most air molecules are being pulled by gravity downward. So they have an acceleration downward. So that provides a weight to the atmosphere. So that is the force. So that is what we get the weight from. So Dalton's law is very simple. Every type of gas that's in the atmosphere exerts some kind of a pressure. And when you add them all up, that's the total pressure of the atmosphere. Each individual gas exerts its own individual pressure, and the total is what we call air pressure. So, air pressure depends on the mass of the molecules, how heavy they are, or how many they are, and the kinetic energy, molecular energy in the molecules. So, it's basically the force of gravity exerted on a mass is weight. So why don't structures and all collapse under this massive amount of air pressure that's on them, all that weight of the air above them? Well, we also have the air inside of them. And if you ever think about it, if you got rid of the air inside, you actually can watch. If you pulled out air, sometimes I've seen people do it with little cans or whatever, where they suck the air out of them with machines, and the cans just collapse because there's no air inside. The air pressure just crushes them. There's obviously all kinds of instruments that we can measure air pressure with. Units of air pressure. One of the questions this week is going to talk about why do most people in the United States see it in inches of mercury? Well, if you look at a typical old school barometer, they were made out of a tube which went up, and it was read in inches of mercury. So that is what everybody is used to using in the United States. Nowadays, in the international standard, is millibars. And we use that here in the U.S. if you're looking at a weather map. It's millibars that you're reading it in. So basically, 1 millibar equals 29.53 inches of mercury. So it's just something to think about when you're looking at weather maps and hearing it. You're going to hear me talk about millibars. You're going to see it in the book. And you might even hear it from your local weatherman sometimes, instead of just inches of mercury. So, the air is compressible. So that air that's above you, all the way up through the atmosphere, is pushing down and pushing the molecules closer and closer together, the closer to the Earth it is. So that down here at the Earth, the air is much more dense than if you're on top of a mountain. I used to have some courses out in Boulder, Colorado, when we'd go up to Rocky Mountain National Park. And you can really tell the difference. The wind, when you're up in the park, would be blowing maybe 30, 40 miles an hour, but it didn't feel like it was blowing that hard because the gas molecules were that much further apart so that we weren't getting the pressure. While as the same wind down in the valley, wow, it was a big difference. So you can see that really, these molecules move apart very quickly the further up you go in the atmosphere. So with that, you can see here the curve of air pressure, and with altitude, you can see it really is very quickly. It drops off, and then it gradually just slows down the higher and higher it gets because you have so much mass gone. But basically, half of the atmosphere is below 18,000 feet, yet the atmosphere can go up to 100 miles. So there's a whole lot of very spaced out air up above you. There's a horizontal variation to air pressure too, between lows and high pressure. High pressure, just what it says, higher pressure. Lows, lower pressure. One of the things I wanted to point out, just on this graph, here's 1,000 millibars and 1,028 millibars over here. So there's 28 millibars of difference. If I go up 3,000 feet, or 5,000 feet, let's say 5,000 feet in the atmosphere, the pressure is going to go from 1,000 millibars to 850 millibars. That's 150 millibar pressure difference in 5,000 feet. Here, in 1,000 or 2,000 miles, I'm only getting 28 millibars of difference. So the pressure difference on the surface is significantly less than the pressure difference is in the vertical. Something to think about. It's going to impact the weather in how we describe it. Rising air temperature has an impact on pressure. If you heat a container up, the molecules are going to start shaking more and more. You've added heat, you've added energy to that set of molecules. If you add energy to something, that's going to increase air pressure. So air pressure drops more rapidly with altitude in colder air. Cold air is dense. All the molecules want to come together in a very tight little space. Whereas when you have a lot of kinetic energy, the molecules want to pull apart, so they're not as dense. So, less dense air, Avogadro's law. The more muggy the air is, it can be referred to as heavy, but it's actually lighter than dry air because water vapor doesn't have as much density as normal air. So the more water vapor you have, the less dense the air is going to be. So cold, dry air masses are going to be the densest. That's why in the wintertime, when you have a big, strong, high-pressure system coming down over you, and it's extremely cold up there in Ohio, your air pressures are going to be extremely high. Now, if you have a tropical weather system coming up with lots of moisture and lots of heat, the pressures are going to be much lower. There's another aspect to air pressure. The winds can converge together. Say winds were coming in, we'll just take West Virginia. And if the winds are coming out of the west, hitting the mountains in West Virginia, they're hitting something, they're converging on that mountain. They're getting stopped by it. So where are they going to push the air? The air is going to go downward. It's going to tend to push downward. So you wind up, when the air pressure is getting pushed downward sometimes, you wind up getting convergence. And when convergence occurs up high in the air, it pushes the air down towards the surface, and you wind up with higher pressure at the surface. And if you get divergence at the surface, you pull the air that's been converged above it, downward. So you're going to hear a lot about divergence and convergence over the weeks ahead. And we're going to talk a lot more about that in coming chapters here. The ideal gas law. It relates pressure and density and temperature. If you know two, you know the third. So that is a way of relating the three variables. So expansional cooling, when air expands, the temperature of the gas drops. So if I allow air coming out of a bike tire, and that's the one I love to use, and they use it here, because I feel it. If air is pulling out of that bike tire, it's expanding, or a tire in an automobile, and it's a lot cooler. But if you push it in, you ever feel the handle of the pump, if you have just a regular hand pump, and how much hotter that pump's getting because you're compressing the air? Because that's compressional warming. And these both occur in the atmosphere. So they're both products of energy. Another thing that happens in the atmosphere, if the atmosphere, a parcel of air, and we're going to define a parcel of air as any size. It could be the size of your fist. It could be 500 miles across. But let's just take a parcel of air, and we're going to rise that parcel of air upwards. What happens? It expands, right? Takes up more room. Well, in expanding, it's losing heat. So the air is going to cool. That's why when you go on the top of a mountain, it's cooler. And what rate does it cool? If the air is perfectly dry, it cools at 9.8 degrees Celsius for every 1,000 meters. So, or converting 5.5 degrees Fahrenheit for 1,000 feet. So if you climb a 3,000 foot hill, you're going to be about 16.5 degrees cooler than when you started at the top of that mountain. So if you started at 70, you'd be down in the 50s by the time you hit the top of the mountain. All due to the dry adiabatic lapse rate. Now, we're going to talk next in a few chapters here in the future about moisture. And remember, when moisture condenses, it gives off latent heat. So if condensation occurs, it's not going to cool as fast as under dry conditions because latent heat is being released and you're going to get heating. So you're only cooling about 6 degrees or so for 1,000 meters. I wanted to show you a couple maps here today just talking about pressure. And there is not a lot of pressure change across the entire United States. There's a little low pressure off the East Coast here, pushing down a very weak cold front along the East Coast. Another weak low here, but there's high centered over much of the central part of the U.S., over Ohio and all. So you can see there's not a lot of pressure change, not a lot going on today. If you look above that at the pressure, you can see here 850 millibars. We have some lows. Low pressure down over the Gulf of Mexico and high pressure up over, kind of corresponding to where we looked at on the surface map, really. Low down here along the Gulf. One of the interesting things is you can derive winds too from clouds and all. We're going to talk more about winds in the next section. But I just wanted you to look at the pressure here fields today, get a little feel for them, and we'll discuss these more later when we talk about wind in the next grouping.